All right, then let's move on to section 5.4, which is where we're going to be using a lot of what we learned about logarithms in conjunction with what we already learned in chapter 4 about exponential models. So in a way, this section is going to be actually a lot of review. So it should be, hopefully, very familiar, with the exception that I know that it's story problems, and that always kind of makes people a little nervous. But remember, the story problems in this book we can totally do. We just have to keep our head about us. So let's see. We have example 1. The percentage of U.S. workers who tested positive for drugs has decayed exponentially from 13.6% in 1988 to 4.1% in 2005. Let f of t be the percentage of U.S. workers who have tested positive for drugs at t years since 1988. Find an equation for f. Okay. Well, if we're going to find an equation, we're going to need some points, right? So let's think about this just a little bit. Actually, let me insert a table. Hold on. There we go. Okay, so let's make a table of points for ourselves just to kind of figure this stuff out. So we want t as years since 1988. Now you notice right here, it said it was 13.6% in 1988. See that? So that means when time was 0, we were at 13.6. And then down here it says 4.1% in 2005. Let me give you green for that one. So that means 2005. All right, 2005. Let's see. That would be, let me quit and get out of here. 2005, take away 1988, enter, make 17. So we have 17, 4.1. All right. Okay, so then that helps because then we have our equation. Well, excuse me, we have the bits that we're going to need in order to find our equations. All right. So how are we going to do this? Well, it didn't say to do it by hand, but I'm just going to review doing it by hand, and then I'll show you the calculator as well. So remember that f of t, if it's an exponential, is going to be a b to the t, right? But we also remember that we know what a is. A is the y-intercept, which in this case is 13.6, right? So we know that part already. So all you have to do is find b and you're golden. Okay, well, this is where I'm going to use that other point. 4.1 equals 13.6 b to the 17. All right, now we'll just do a little bit of math here. We'll divide by 13.6 to both sides. Right, if you do it over here, we got to do it over here. All right, make my calculator find that, and this will go away. That's why I'm doing it. Right, make this all disappear. Okay, so 4.1 over 13.6. 4.1 divided by 13.6. All right, 0.3015 roughly. 0.30147. I'm going to keep more decimal places than I really need, but that's because you want to keep more until the very end and then you can get rid of it at the end, right? Okay, so then I want to get b by itself, so I'm going to raise both sides to the, remember from chapter 4, the 1 over 17 power. You do it to the left, you got to do it to the right, keep everything fair and copacetic and all that good stuff. So I'm going to make the calculator do that. So I'm going to raise it. It'll take my last answer, which was that 0.301 blah, 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 and I want to raise it to the 1 over 17. Right? And again, remember, if you don't have the new system, you're going to need to put parentheses. Anytime you put a fraction up in an exponent like that, if it still has the little caret symbol for you, then you're going to need to use parentheses. So you have to go parentheses 1 divided by 17, close parentheses. If you have it up in the superscript like mine does right here, where it's like above the line, then you're fine and you don't need parentheses. But if it does the little caret symbol thing, you're going to need parentheses because you should come up with 0.9319 roughly. Okay, so 0.9319 is approximately b. And there we go, we have our equation. F of t is equal to 13.6, because that was our a, times 0.9319 to the t. There it is. Now, as with most things in algebra, we actually can check ourselves. Remember, you guys have a calculator. You paid good money for it, or you stole it from a relative. I don't know. All right, so if I go to Stat, go to Edit, clear out this old stuff from an old problem. Go over here, clear. There we go. And I type 0, 17. Oops, not 117, 17. And then I go over here to 13.6, 4.1. Stat, calculate. Linear regression is not what we want. We want, where is it? There it is, exponential regression. He's what we want, 0 on my calculator. So you say exponential regression, press enter, and it should be the same numbers you came up with. And it is, see? 13.6 is your A, 0.9319 is your B. Ignore the R's, that's because I use my calculator for statistics. But if you're in algebra, you don't need to pay any attention to that. And your calculator probably doesn't even do them, and that's totally fine. All right, don't worry about it. All right, so there we go. We confirmed it, and I'm going to put a little picture in here. So that way I remind myself, you know, like many things in algebra, you honestly can double check yourself almost at all times with a calculator. It's just that you can't use the calculator alone to find your answers. Cool, we're done with that. All right, now that we know that, let's find f of 20 and find what it means. And of course, that's actually going to be quite simple. It would have been easier on myself if I had stored this equation. So I'm going to go do that. Stat, calc, 0 right here. And I'm actually going to store it by using variables, y variables, function number 1. And remember, if you have the new systems, it might ask you what's your x list, which is L1, what's your y list, which is L2, and then somewhere it'll say store EQ, store equation. You can do the same thing. You press variables, you move to y variables, you pick number 1 function, you pick whichever one you want. Usually it's number 1. All right, so why did I do that? Well, because then it has my lovely equation with 13.6 and all that jazz. It has it right in there. So if I go to my table, I can see when what happens when x is 20 really simply. I mean, it's either that or you can type it yourself. So it looks like it's 3.318 right there. Or you could do it this way. You could say 13.6 times 0.9319 to the 20. Like that. That'll work as well. All right, so let me write that up. F of 20, not g of 20, good grief. F of 20 is equal to 13.6 times 0.9319 to the 20, which is about 3.318. Cool. All right, so then, of course, we always have to explain what that means. So now remember, this was T for time, right, in years since 1988. And then the F of T was the percentage of U.S. workers who have tested positive for drugs. So in 2008, right, because 1988 plus 20 makes 2008. If that confuses you, you can always double check yourself. 1988 plus 20, enter. See, 2008. So in 2008, the model predicted that about, or the model estimated, I should say, because it's in the past, not the future. So estimated that about 3.3184% of U.S. workers tested positive for drugs. Cool. Next. All right, because you might be wondering, well, wait a second, Alana, none of this sounds new, and you'd be right, right? None of this is new. Everything that we've done so far is actually review from Chapter 4. Literally, all of this is stuff we did in Chapter 4. It's just not this particular problem. But nothing in this involved Chapter 5, which is inverse functions and logarithms. So where does Chapter 5 come in? Well, it comes in right here. This is a question you couldn't do in Chapter 4 because, let me show you why. It'd be 2.9 equals 13.6 times 0.9319 to the t. Notice where your variable is. Matter of fact, I'm going to put it over here. Right? The variable's in the exponent. There is only one way to do this, right? So there's only one way to get a variable out of an exponent, and that's a logarithm. You have to take the log of this. But you can't do it right away. Remember, you can't take logarithms when it's this big mess. You have to get the thing that's raised to the power by itself first. So we're going to have to divide both sides by 13.6. That's going to cause this to disappear. Okay, so we're going to have 0.9319 to the t is equal to roughly, let's see, 2.9 divided by 13.6. Enter. 0.2132. All right, let me do squiggly equals because we're now into rounding territory. We kind of were anyway, but we even are more now. Now, the big mistake students make here is they're like, oh, I want to get rid of 0.9319, so I'll just divide. No. Division is the opposite. It's the inverse of multiplication. So I do it up here because this is multiplication right in here between that 0.6 and that number. That's timesing. So I divide because that's the inverse function of timesing. But down here, this isn't timesing. This is raising it to a power, an unknown power at that. So that means we're going to have to take the log of both sides. That is the only way to do this. So you take the log of 0.9319 to the t is roughly equal to the log of 0.2132. You're taking the log of both sides. And you're thinking, Alana, that does not make it easier. That's a mess. Well, no, it's not. Because remember that when you do this, you can bring that t down in front. So it becomes t log of 0.9319, like this. That's the power property, right? So you take the logarithm because that allows you to bring that variable down in front and multiply it. But wait, that's multiplication right there. So multiplication, the inverse of that is division. So what we're going to do is we're going to divide both sides by the log of 0.9319. Whatever the heck that is. I mean, it's just a number on your calculator. It's not like, you get to know what it is or anything, right? So that'll make the whole log thing. Here, let me make it go away. It'll make it all disappear. Okay, on that side. So all I've got to do is make my calculator find this part, and I'm done. So let's see. The log of that number, 0.2132, blah, blah, blah. Close your parentheses for sure. Then divide it by the log of 0.9319. There you go. It's about 21.9. So t is approximately 21.9. All right, we did it by hand. Now you're thinking, well, how would I have not done it by hand? Well, you could put this into y2, right? Y equals. You have your equation in there for y1. You could put y2 is 2.9, and you could find the intersection point. That's another way you could do it, right? Although it wouldn't actually be on my particular graph because I don't have they're not on screen. I don't get to 21. But that's how you could do it. See, they never get there yet. But if I change my window so that I'm going to 25 here, then I graph. Then you'd be able to do it by hand or with your calculator. And if you do it by calculator, then it should intersect at the same spot you found. So if I go calculate intersection, enter, 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 there it is, 21.9. It was the same as what we had found. Oops, it disappeared. I don't know why I did that. There you go, 21.9. So you can back yourself up always with your calculator, right? I'll even throw that in there real quick. Okay. Now, what does it mean? Well, that's a different story. Hold on, I gotta make a table. There we go. The model estimates that about 2.9% of U.S. workers tested positive for drugs in about 2010, because if you round it to 22, 22 plus 1988 makes 2010.